Welcome everyone to the Spring 2021 webinar series. The session for today, IRT for Forensics, a reanalysis of the FBI black box study. Today your speaker is Amanda Luby. Amanda comes to us from Swarthmore College, where she is a professor of statistics by way of Carnegie Mellon, where she has done a large portion of her study. Amanda's focus is really research in statistical methods for understanding complex human decision making. And she actually has been with us at CSAFE since the very beginning. So we're very excited to have her as our presenter for our webinar today.
All right. So today I'm going to be sharing some of my work on IRT for forensics, kind of within the context of analyzing the FBI black box study data. Most of what I'll be talking about today is from a paper that was published last year in Behavior Metrica. This is available both on the CSAFE repository and also freely available open access from the publisher. And before we get started, I just want to take a moment to acknowledge my awesome collaborators and co-authors, Brian Junker, who's in the Carnegie Mellon Statistics Department, and Anjali Mazumdar, who is at the Alan Turing Institute in London. And so I'm assuming that most of the people who are here today are familiar with this black box study that was run by the FBI and Noblis. This was done in 2011. So as a little bit of a refresher, the main goal of this study was to estimate casework error rates in latent fingerprint comparisons. There were 169 participants. It was open to practicing latent fingerprint examiners in the community. There were a question pool of 744 items. Each item was a one-to-one comparison, and the prints came from known sources. And so this is a case where we do have ground truth for the items. Each examiner saw roughly 100 questions. Participants were given several weeks to complete the exam, and the test conditions were not controlled. So the main results of this study were to provide estimates for the casework error rates. There's two types of error rates. The first is the false positive rate. And so these are individualizations when prints came from different sources. And these can lead to innocent suspects being prosecuted. And so within this study, this was estimated to be 0.1%, so 1/10 of 1%, which is very, very small. And the other thing I just want to mention is that I know that the word individualization is maybe not used quite as much as it was when the study was run. And so I'm going to use it throughout this talk just because that's the way that the data was recorded that I'm working with. The other type of error rate is the false negative error rate. And so these are exclusions when prints came from the same source. And so these types of errors can lead to guilty perpetrators going free. And so within this study, this was estimated to be 7.5%. And so, of course, there are many other results within this study, but these were the main estimates of the casework error rates. And so one of the first things we started to think about when we were kind of revisiting this data a couple of years ago is what is the variability like among the examiners who participated in this study? And so one of the first things we did is look at, okay, what's just the percent correct of decisions for each examiner. And so here we have a little graph. Each point is a participant in the study. And on the x-axis, you can see what their percent correct score was. The participants who made a false positive error are shown in green. And so one of the first issues that we run into is that it's really hard to directly compare the percent correct scores since different participants saw different items. And so it's not really fair to compare percent correct or compare error rates when the different participants are seeing different questions, and some questions might be lower quality or higher quality than others. And there's really no way to immediately adjust for that if we're just looking at the percent correct. And so the proposed solution that we came up with is item response theory. And so my one slide introduction to item response theory is that these are a class of statistical methods that are often used in educational testing. And so it's really common in educational testing for students to sit for different versions of the same exam. So you can think about the SAT, there's different versions every year that are offered. And so students are seeing different questions, but given scores that are meant to be on the same scale, even though some students might see questions that are harder or easier than others. And the underlying idea is that we will model the probability of a correct decision based on participant proficiency, which we call theta, and item difficulty, which we call B. And so this is a really powerful method for accounting for differences among the participants and kind of separating out those effects from the item effects. And so this allows us to account for participants answering different subsets of questions and maybe seeing a subset of items that were harder or easier than others. And so the method that I'm going to be using a bunch today is the Roche model. And so here we model the probability of a correct response, which is y equals 1, with the inverse logit of the difference between participant proficiency and item difficulty. If there are statisticians in the audience, you will probably recognize this as a random effects logistic regression. And so what this looks like is really just a curve. And so here I have shown you the probability of a correct response on the y-axis, proficiency on the x-axis, and then this curve in blue represents a question. And so we can see that for this particular question, which has a difficulty equals to 0, we can see that as proficiency increases, so does the probability that you get the question right. And when proficiency is equal to difficulty, the probability of getting the question right is 0.5. If we have an easier question, that corresponds to a negative difficulty. And so we can see that it is more likely that participants of all proficiencies get that question right. And then if we have a harder question, that corresponds to a higher difficulty or a positive difficulty. And so we can see that you really need to have an increased proficiency in order to start increasing your probability of getting the question correct. And so if we go ahead and apply this to the black box study, we see that the estimated proficiencies, so these theta estimates, really do correlate with the error rates. It's kind of hard to see in the left-hand graph. So I have proficiency on the y-axis and then the error rates for each examiner on the x-axis. And so there's so few false positives that it is really hard to see any trends in this left-hand graph. But in the right-hand graph, we can see that as the false negative rate is increasing, the proficiency is going down. So if people make more errors, they get a lower proficiency estimate in general. And so this is great. This is exactly what we would want. But we also see that this isn't a perfect line. And so there's some variability around the line. And so the error rate or the percent correct isn't totally determining this proficiency estimate. And so now, again, this is a really similar graph, but we have the observed score on the x-axis, the proficiency estimate on the y-axis. And so we can see that as the score increases, so does the proficiency estimate. But now I've highlighted all of the participants who scored between a 94 and a 96% on the black box study if we were just counting up all of the correct decisions. And so it's really hard for, to distinguish just based on score what these if there is any differences among these examiners. But we see that there's a pretty big range in the proficiency estimates that they're given. So all the way up to 2.5 and all the way down to maybe -1. And so this is a really big range of proficiencies for people who had the same percent correct score. And the reason that they are getting different proficiency estimates is because they saw different subsets of questions. And so these are the same examiners who are in purple. Now they're over here on the right graph. But I have plotted the average question difficulty that they saw on the x-axis. And so we can see that as the average question difficulty of the pool of questions that they answered goes up, proficiency also tends to go up. And so people who saw harder questions are getting higher proficiency estimates than those who saw easier questions. And the other thing I want to point out is the color here also represents the percent conclusive. And I see there is a question in the Q&A about inconclusives, and so I will get to that just on the next slide. And so we can see that in general, the more often that examiners are conclusive, the higher proficiency estimates that they're given. And so it's kind of implicitly accounting for those inconclusive responses without kind of explicitly putting them in the model. And there's also a question about how is theta determined. And so this is really an estimation method that just looks at for each participant and for each item, how did other people respond to that question, and then kind of trying to average out those effects and sort of separating out effects due to the examiner and then effects due to the item. And I can talk more about that at the end. And so I mentioned the inconclusives in the last slide. And so I think this is a good time to dive a little bit deeper into what the black box study actually measured. And so here's an example item, kind of a made up example of what the questions looked like. And so the first task that examiners were asked to do is to evaluate a latent print alone. And so within the study, they could say this has value for exclusion only, value for identification, or no value. For this analysis, I've pooled value for exclusion only and value for identification into one category, sort of to try to deal with some inconsistencies in the data. And then they could also say that it has no value for source decision. And so if it said that they had no value for source decision, the question was done and they went on to the next item. If they said it did have value for a source decision, then they were shown the reference print alongside of it and asked to evaluate whether or not the prints came from the same source. And so here they could report an individualization, so the prints came from the same source, an exclusion, so prints came from different sources, or an inconclusive, and so that there isn't enough information either way to tell. And there's actually a ton of information in these responses, because in addition to these source decisions, we also have the reason for the decisions if they didn't make an individualization. So if examiners made an exclusion, they could say that this was a pattern exclusion. So they used the overall ridge patterns to determine, or they could report a minutia exclusion. And so they had to go into the more detailed information in the print in order to make an exclusion. If they reported an inconclusive, they could say either close, so there is corresponding area between the two prints, but not to the extent needed for individualization. They could report a no overlap, and so there was no overlapping area between the latent and reference print, or they could report insufficient information, which was kind of a catch-all reason for an inconclusive. And so I have pooled the no overlap and the insufficient information inconclusives into a single category to kind of represent the general inconclusives. And then finally, they also reported the difficulty of the question on a 5-point scale. And so if we start to look at the variability in the decisions, there's actually a lot of variability in the inconclusive and the no value decisions. And so again, here we can see each examiner's responses and how many times they were inconclusive on the left and how many times they reported no value on the right. And so we can see that most people who participated in the study reported between 20 and 40 inconclusives and roughly between 10 and 30 no value decisions, but that there's a huge range of the number of responses. And so some examiners reported less than 10 inconclusives and some examiners reported over 50. And so again, this is where it comes in that we know that examiners saw different subsets of fingerprints in this study. And so it's really hard to make a direct comparison here on the number of inconclusives or the number of no values that different examiners were reporting, because we can't directly compare them because they all saw different subsets of prints. And so this kind of brought me to thinking about how could we score these inconclusives in order to include these responses into an item response theory model. And so my first thought was we could treat them as missing at random. And so this is what was used to calculate the casework error rates. And so that is a pro of this method. But we end up ignoring about 30% of the overall responses. And so as a statistician, I didn't want to ignore that much data, and so would really prefer to keep them in there. I also thought about scoring them as incorrect. And so this penalizes examiners who are inconclusive very often, but it may actually be the correct response for low quality prints. And so treating every inconclusive as incorrect also wasn't what I wanted to do. Within the item response theory framework, we could also treat the inconclusives as partial credit. And so this is nice because it distinguishes between errors and inconclusives, but it still doesn't account for when an inconclusive is the correct response, when the print is very low quality, or there's not enough information in between the latent and the reference print to come to a conclusive decision. And so we really don't want to penalize examiners for that. And the more I looked at this, the more I kind of thought of these ad hoc scoring methods. So things like using consensus answers, using the best answer. So if any examiner came to a correct individualization or exclusion, then that would be considered the correct response. And so on and so on. The more we think about this, the more we can come up with different scoring methods. And these kinds of issues have also been raised in some recent papers, sort of thinking about the relationship between inconclusive rates and error rates. And so it is kind of a hard problem, and it's not immediately clear what should be done with these inconclusives. And so the main part of what I want to talk about today is, what if we don't do any scoring? So what if we don't treat anything as incorrect, anything as correct, and we just look at the decisions that were made and try to model them within this framework? And so the approach that I present here is based on 3 ideas. The first is that it's important to better understand the variability of decisions among fingerprint examiners. The second is that it's unclear how inconclusive and no value decisions should be treated in the error rate framework. And then the third is that fingerprint comparison is a complex task, and proficiency is multidimensional. And so anytime that we are trying to summarize proficiency with a single number, we're going to lose some information. And so really what happens if we approach this in a multidimensional way? And I just want to mention that these are similar goals, but a different approach than a recent paper in Forensic Science International by Hicklin et al. And so the basic idea behind the model that I use is to use a decision tree for each of the responses in black box data. And so this is the IRTs framework of DeBach and Parchev. And so for each examiner item response in the data set, we are going to model 5 different decisions. And so the first decision is whether it was a no value or not a no value. The second decision was it a pattern exclusion or not a pattern exclusion? The third decision that we model is kind of a match tendency. So it could be closer to a match or closer to a non-match. If it's closer to a match, then the fourth decision is either an individualization or a close inconclusive. And then if it was closer to a non-match, the fifth decision is exclude based on minutia, so the lower level detail, or an inconclusive. And so if we want to model the probability of any response in the data set, we can just multiply those probabilities. And so the probability of a close inconclusive is the probability that Y1 is 0, Y2 is 0, Y3 is 1, and then Y4 is 0. And so I really want to mention that this is not the only decision tree out there, and that different people are going to be using different decision trees. And so really how I came up with this tree was using the process map from the OSAC friction ridge subcommittee. If you're familiar with the paper that I'm using, this is a slightly different tree from the version in the paper because the process map was officially published after we had submitted the initial draft. And so if we kind of go through and pick out certain decisions in this process map, Y2 represents, can I exclude based on level 1 detail? Y3 is, does data support same source more than different source? Y4 is, are the data sufficient to the exclusion of all others? And then Y5 is, does the data support different source more than same source? And so I'm of course not saying that this is the one and only true way to construct a tree, but since the process map was constructed to capture current practice, it is kind of a good approximation of an average decision. And I see there is a question for the paper reference from Hicklin. And so I have the full citation, I believe, at the end of the slides. And so that should come up eventually. And so here for each participant, the model estimates 5 parameters. The first is a no value tendency. The second is a pattern exclusion tendency. The third is a lean match or non-match tendency. An individualization tendency is the fourth, and then a minutia exclusion tendency is the fifth. And so what I really want to emphasize about these estimates is that these are examiner estimates after accounting for the items that they saw. And so it's after accounting for what we would expect for the subset of items that they saw. And so if we start to look at what each of these proficiency, or not proficiency, each of these IR3 parameters look like, I think it's kind of helpful to start to compare them to the percent correct if we just used the error rate type scoring. And so on the y-axis here, I have the estimated tendency for each of these decisions in that tree that I presented. And then percent correct is on the x-axis. And so we can see that there's a slight positive relationship here. And so examiners who tend to have higher scores also tend to make more no value decisions. And so maybe they're filtering out those low quality prints kind of earlier in the process. And so we can continue to do that for every theta estimate in the tree. I see there's a lot of chatter in the chat, and I'm not able to keep up with it. And so I'm hoping to come back to a lot of it in the Q&A period, but I apologize if you asked a question and I have missed it. And so I'll just leave this up for a second because we can think of it as showing how these theta estimates are related to percent correct. And so what I really want to point out here is what the variability looks like in these different decisions. And so theta 1, which are the no value decisions, and theta 4, which are the individualization versus close inconclusive tendencies, are the most variable. And so these are the estimates that are furthest away from 0 and tend to be more extreme than the other theta estimates. And then I also want to point out that theta 3, which is that whether it's closer to a match or closer to a non-match, is often what we think of as proficiency. We often think of it as the ability to distinguish between matches and non-matches. But when I look at this data, this is actually the least variable among examiners. And so this is actually not where most of the variability in examiner decision making is happening, according to this method of analyzing the data. And so a natural next question might be, how are the tendencies correlated? And so here I have the correlation coefficients for each of those theta estimates compared to each other. And so first, I'll point out that examiners who are likely to individualize are also likely to exclude. So if you are conclusive in one branch of the tree, you're likely to also be conclusive in the other branch of the tree. This minus 0.54 tells us that examiners who are likely to rate items as has value are likely to use more inconclusives further along in the tree. So people at that first branch who use has value more often than the average examiner aren't magically coming up with conclusive decisions later on in the tree, but they're reporting more inconclusives there. And so these should kind of make intuitive sense if we think about how that tree was constructed. I also think that the lack of correlation here is also interesting. And so here, these are the correlations with theta 2 compared to the other parts of the tree. And so these are all really close to 0. And so these tell us that examiner tendency to make pattern exclusions doesn't tell us much about the other decisions in the tree. And so this is kind of an independent process of the other decisions that were made in the tree. We can also do the same thing for the items. And so the first thing I'll point out is that we have some strong correlations in the middle part of the tree. And so I think this is probably due to the conditional structure of the tree. So items that are likely to be rated as exclusions in that second branch are also likely to be rated as exclusions later, and so on and so forth. But perhaps more interestingly, again, items that are likely to be rated as no value also tend to be rated as inconclusive later on in the tree. And so I think these are useful to talk about because these correlations kind of match what we might expect if we think about kind of projecting this decision tree onto responses in the black box study. The results that we're getting are kind of consistent with what we imagine might happen on average. Another thing that these results are useful for is we can predict responses based on results. So for example, examiner 55 reported a close inconclusive for item 556. And so based on the results from the model, we can estimate probabilities of observing a no value, a pattern exclusion, an individualization, and an inconclusive are all very small. The probability of observing a close inconclusive was estimated to be 0.125, and then the probability for a minutia exclusion was estimated to be 0.851. And so here, this is an example of where the model is expecting a different answer than what was given in the black box study. And so I think this is, a useful way to kind of think about flagging responses as surprising and try to, better understand why for this particular examiner item pair, did we observe something that the model didn't expect. And it also suggests a way to more systematically kind of look at the performance of examiners overall. And so if we kind of think about, generating an answer key, and so I put answer key in quotes here because I'm not really interested in giving out scores, but more sort of figuring out what the responses are expected to be for each item. And so here what I'm doing is for each item, trying to gauge how does the model expect an unbiased examiner. So if all the thetas are equal to 0 and there's no examiner tendencies at all, what do we expect for that item? And so for the 744 items, we obtained the following answer key. So 177 of the 744 items are expected to be no value, only 15 pattern exclusion, 176 individualization, 25 close inconclusive, 190 inconclusive, and then 161 minutia exclusions. And so in the paper, I kind of mentioned this, and this is more for the stat crowd, but this approach is closely related through the conditional sufficient statistics to other methods for test theory without an answer key. And so if we did score examiners based on this answer key that we come up with, we get really similar scores to if we use a modal answer key. And so another way to think of this is that if we score responses based on the IRT results, we basically get a score based on consensus answers. And so instead of thinking this as a score or a percent correct, maybe a better way to think about it is how often each examiner is matching the consensus answer. And so the other thing I want to point out is that this does result in technically lower scores than the original scoring. So most of the original scores, if we're not incorporating inconclusives or no values at all, are pretty high. And so in general, if we are scoring based on the consensus answers, we get lower scores in general. And so again, I really don't care about these scores, and I'm not trying to score the responses, but I think that this is an interesting comparison. And really what I want to point out is that there are these two examiners. So examiner 95 is this top dot, and then examiner 3 is this lower dot. And so both of these examiners had 100% correct if we are just using the error rate scoring. And so they didn't make any false positive errors and they didn't make any false negative errors. But if we're using the IRT and kind of consensus-based answers, they get extremely different scores. So examiner 95, is up here at like 85%, and examiner 3 is closer to 50. And so this is a huge discrepancy. And so what I think the IRT method is really powerful for is doing a deeper dive of why those differences are occurring. And so this allows us to directly compare the examiner estimates, and these estimates already account for the different subsets of items. And so we can see that examiner 3 tends to make more no value decisions, fewer individualizations, and fewer exclusions than examiner 95. And so this is kind of why we're seeing that discrepancy in the consensus answers or the consensus scores, is because that examiner is making more no value and inconclusive decisions. And I also want to point out that examiner 95 here is really kind of an ideal examiner. So remember that they made no false positives and no false negatives. And we can see here that they also don't really tend to make a ton of no value or inconclusive decisions either, because all of their estimates for these parameters in the tree are pretty close to 0, which is kind of what we want. And so effects about the items are really driving most of their decision making, and they don't really have any tendencies after accounting for those item effects. And so I want to wrap up just by talking about a couple extensions that I've been working on. And so the first is incorporating print characteristics. And so one of the things I'm looking at is, can we explain item tendencies with covariates about the latent reference pair? So we have I've included 3 variables about each of the items. And so first is whether the prints were from the same or different sources. Second is the image quality, and third is the image clarity. And both of these come from the LQ metric software. And so really what we can do is we can model the item effects using a linear model, which depends on both clarity, quality, and source. And so these metrics are also described in the 2013 Assessing Quality and Clarity of Latent Prints paper. And so if we look at these estimates for that first split, so for the no value versus has value split, we see that for higher quality and clarity metrics, items are more likely to be rated as has value. So this shouldn't be surprising, but it's kind of a good sanity check that the results that we're getting kind of make sense. If we look at the same estimates, but for Y4, so that individualization or close inconclusive split, we see that higher quality and clarity metrics are associated more with individualizations than with close inconclusives. So this is also expected. And we also see that when items really do come from the same source, they are more likely to be rated as individualizations. For Y5, similarly, higher quality and clarity tend to be rated as minutia exclusions. And then interestingly here, items that are same source are more likely to be rated as inconclusive. And so this should also make sense. So when items are the same source, they're not likely to be rated as minutia exclusion. And so really what I want to stress here is that there's nothing especially surprising about these results. So higher quality and clarity metrics are associated with fewer no value decisions, more individualization over close inconclusive, and more exclusion over inconclusive. And so these results could be used to identify items for further study. So what is it about items that make, so if we are predicting the item effects using only the covariates and we're estimating something that's way off from that, what is it about those items that makes examiners respond to them differently than prints with similar quality or clarity metrics? And so I think that this has the potential to relate to some other CSAFE work that's going on quality metrics. And so the next thing I want to talk about is incorporating reported difficulty. And so if you remember all the way back when we talked about an example question in the black box study, the last thing that examiners reported was a reported difficulty on a 5-point scale for each item. And so we can use the same IRT framework to also model this reported difficulty. So the probability that examiner I rates item J as very difficult, we can use a logistic regression model. I'm cheating a little bit here because this is an ordinal logistic regression model, and so we're also estimating some cut points, but this is the main idea. And so examiners who are estimated to have positive H tend to overestimate the difficulty relative to other examiners and the items that they saw. Examiners with negative H's tend to underestimate the difficulty. Items with positive F's tend to be reported as more difficult than we would expect. And then negative F's are items that tend to be reported as easier. And so what I find really interesting about these results is that the reporting tendencies that we estimate for examiners are not related to their scored performance. And so on the y-axis here, we have those reporting tendencies. And so positive values are more likely to overestimate the difficulty, and negative estimates are more likely to underestimate the difficulty. And then I am showing that relative to both the error rate scoring and then also the scoring in the IRT or the consensus-based scoring. And so in both cases, these tendencies are both different from zero. So there is variability in how examiners are reporting the difficulty, but it's not related to how they're performing. And we can do the same thing and look at the reporting tendency related to the other thetas that we estimate in the tree. And so maybe one of the things that we would expect is that, examiners who are inconclusive more often maybe are reporting or estimating the difficulty to be more difficult than it is. And so here we really don't see any strong relationships. There may be some slight negative relationships for theta 4 and theta 5. And so folks who are conclusive more often may also be underreporting the difficulty of items. So maybe they are just a little bit more used to seeing low quality items and don't interpret them as difficult as other people in the study. And so finally, some conclusions and implications here. So first, IRT provides more information than the traditional percent correct scoring because we are accounting for both the proficiency, so the participant effects, but we're also accounting for how difficult the particular subset of items that each examiner saw was. We can also model the decision-making process overall using a tree. And so this is really useful because it tells us where that variability is most likely to occur. And so here we found that it wasn't really in distinguishing between closer to a match or closer to a non-match, but more in making those no value or inconclusive decisions, and that this is after accounting for the effects of the items that they saw. We also found that differences in how difficult items are reported to be do not appear to be related to the source evaluation decisions or to the overall performance on the exam. And so I kind of want to close with saying that I think IRT has a lot of potential in forensic science. It could be used in other pattern matching disciplines or other disciplines where we want to gauge variability in examiner effects. It can also be used for proficiency tests or for other black box studies, and that these results really underscore the importance of understanding, the cognitive factors involved in latent print examination, because there is variability here, and it is interesting to look at, even if we're thinking about it, outside of the general framework of correct or incorrect decisions. And so I think I ended a few minutes early. So thank you so much for your time and attention. I have some of my contact information here on this slide, and so I'm happy to hear from you if we don't get a chance to answer your question. And here are also some of the references that I mentioned.
Thank you, Amanda. At this time, I'm going to leave it up to you. If you'd like me to read the questions or the comments to you, I can. Otherwise, you are welcome to address them as you feel appropriate.
Perfect. So I think I will start at the top. So I believe this was back in looking at the tree. And so I apologize for not getting to this at the time. Yeah, and so Eric says that this is not an accurate representation of latent print decision tree. Excluding so quickly based on pattern leads to exclusion errors. And so I really want to emphasize that this is one of many possible decision trees, and that I was really using what might be true for the average examiner, or what is most similar to might be done in practice. But I of course recognize that this is not entirely true for every examiner for every decision that they're making. Oh, a clarification from Heidi Eldridge. The OSAC process map was constructed to reflect the full range of current practice. It is meant to be inclusive. It does not necessarily represent average practice nor most prevalent practice. And so I think that is maybe what I mistakenly referred to. So thank you, Heidi. Oh, so it looks like there is a good discussion on the exclusion reasons, so pattern versus minutia, and then the different inconclusive reasons. And so recommending to be viewed cautiously because they may not be used in many labs. And so a few people are chiming in. So particularly, I'll raise up what Deborah Smith said, that this is a common problem regarding language between agencies and even between analysts. And so, yes, I recognize that this is a common issue in forensic sciences, that different labs and different agencies are referred to decisions in different ways. And so I'm not endorsing one set of reasons over another. I'm just using what was recorded in the black box data, which was this really careful and thorough study, and that I think is really the best decision-making data out there when it comes to looking at a broad swath of examiners. Karen mentions, thank you for the nice talk. I like the idea of incorporating quality and clarity into beta. And so asking about which of the quality and clarity output values from LQM did we use? I should mention that I maybe don't have all of the LQM values. And so there was a quality, overall quality, overall clarity. Sorry, I'm just trying to scroll to the right place. I apologize if I'm making anybody dizzy. And so there were also two for estimates of VID or VIO. And so those are the two that I didn't use. And so these image quality and image clarity are the overall measures from the LQM software. Yeah, so there's a great question here about using the Roche model and assuming that all print items have equal discriminability. So if we are thinking, and I'm going to scroll all the way back here to when I talked about the Roche model and kind of showed those curves, and I'm forgetting exactly where it was. So here we go. And so in the Roche model, all of these curves kind of have the same slope. And so a common method in psychometrics to kind of incorporate a little bit more variability among items is to use a different discrimination parameter. And so this lets the slope of these lines vary. And so I think that would be a really nice extension. I focused a lot more here on including the entire decision-making process rather than trying to work within this binary framework of correct and incorrect. And so I think that if you were to explore more thoroughly, validated psychometric models for correct and incorrect decisions, that would certainly be a way to go. The reason that I didn't use discrimination parameters in the IRT framework is because there just isn't a lot of data. And so we're already estimating 5 parameters for each item and 5 parameters for each person. And so adding more parameters there kind of runs the risk of making the estimates unstable. And so that is the reason that I use the Roche model. There's a question about correlation between estimated examiner proficiency scores and the 7.5 false negative rate. So the false negative rate, that 7.5% was the aggregated error rate. And so it really has nothing to do with the individual examiner scores, or the false negative rate is kind of over all of the examiners. And so I guess we can look at so any particular examiner. Most examiners had false negative rates that were less than the 7.5, but there were a few that were kind of raising up that average. There's a question about whether ordinary error rates have any use or reveal anything. I don't really think that I'm qualified to answer that. I think that aggregated error rates, probably have a role in saying something about the overall field or an overall process, but they're maybe not appropriate for assessing this variability that we're talking about. So there's a great question about the multiplicative probability in the tree. And so I will just scroll to that. Yeah, and so the thing that I didn't include here, just to kind of try to keep the slide as clean as possible, is that each of these nodes are conditional on the nodes that came before. And so we aren't really assuming independence, but we're assuming conditional independence given the decisions that were made. There's a question here about the number of participants that are required for IRT. And so I will just point out that this is the part of the reason why these error bars are maybe a little bit larger than we would expect in a standard IRT setting. And so, if we did have 500 or 1,000 or 10,000 or 20,000 participants who were answering each question, these error bars would go down. And so that's kind of the trade-off that we make by not having the traditional number of participants for IRT.
Amanda, I'm going to ask you to pick maybe two more, and then I want to make sure that I leave just a couple minutes to make some notes at the end.
Great, thank you. So there's a question, when you looked at the complexity difficulty of items, were you able to evaluate the effect of coincidental similarity? In other words, were folks provided with close non-matches, and what effect, if any, did those have? So I would say that that is, part of the data that I don't really have access to. And so it could have certainly had an effect, but the items aren't tagged as, this was intended to be a close non-match, and this was intended to be kind of an obvious exclusion. And so that is something that I don't really have in this data. And then, so I guess the last question that I will answer is on the identifiability and stability of these parameter estimates. And so I will say that they are identifiable. So there are some identifiability constraints that are built into the estimation of the model. So for instance, we assume that the average, that thetas are drawn from a distribution with mean 0. And so that lets everything be identifiable. And that they are relatively stable. I've played around with a few different trees. So if you take a look at the paper, we kind of fit a couple different trees than the one I presented here. And so the estimates kind of vary a little bit. And in particular, the uncertainty estimates change a little bit. And depending on how the tree is constructed and that conditional structure of the tree sometimes changes the estimates, but particularly in the no value and then the individualization versus close inconclusive, and then the kind of match-ish branch and non-match-ish branch, those are all relatively stable. And then the other estimates kind of depend on like which buckets we put the responses into.
Thank you, Amanda. I really appreciate you taking the time and the energy to provide this information, this presentation for us in our webinar today. And I also want to thank all of you for participating today. If you have any questions, you're welcome to reach out to us. We're always happy to answer them. Thank you all, and we hope you have a great day.